Now we will look at some examples. First, we ascribe priorities to the four substituents. Next, we need to view the molecule from the opposite side to the lowest priority, 4. How can we imagine this? Well, in our heads, we need to rotate the molecule as drawn here to having the hydrogen away from us. It sounds painful, and it certainly is a skill that often needs work. The trick, if you will, is to determine what needs to move where and how the rest of the molecule would move with such a key relocation. So here, as we said, we need to move the hydrogen to the back. The rest of the molecule will passively move to maintain the tetrahedral structure. So the carboxylic acid also moves back, the amine nitrogen moves forward, and the isobutyl group stays approximately in the same place, if anything, moving slightly forward. Now, this is a new depiction of exactly the same molecule viewed from the opposite side to the lowest priority, hydrogen, which is ideal for calculating the R or S descriptor through Kahn-Ingold-Prelog rules. Let's put the priorities back again. Now, we're not worried about the lowest priority, hydrogen. Next, we're going to draw arrows from the highest priority to the second highest priority on to the third highest priority. The arrows are going anti-clockwise, so the descriptor is S. So this is the amino acid leucine. Its IUPAC name is S-2-amino-4-methyl pentanoic acid. What's the minus sign about? Well, it reflects the polarimeter reading that generates an alpha value of minus 10.8 degrees. So we're going out of our way to reposition the molecule to make this calculation. Is there an easier way to deal with molecules depicted in an unideal orientation? Well, let's have some fun. And if you think this is fun, you have a very strange idea of fun. We will move the lowest priority group, so hydrogen, to be the closest to your eye. Now, of course, we wouldn't normally deliberately do this, but let's see what happens. Let's move the hydrogen from being in the plane to facing out towards us. Thus, the carboxylic acid will move back, and the nitrogen will move across the back face from left to right, with the isobutyl group staying in the same place. There. Now, let's apply the substituent priorities. Okay, but how are we going to work out whether the descriptor is R or S, with the lowest priority completely in the wrong place? Well, the good news is that the lowest priority is completely in the wrong place. That's to say, the opposite of the ideal place. We don't need to reorientate the molecule. So we create arrows from the highest priority through the second highest priority on to the third highest priority. We are looking at clockwise. So normally this would be R, where the lowest priority is furthest from your eye. But the lowest priority is opposite, nearest your eye. Thus, only now a clockwise rotation gives the opposite result of S. What about this molecule? Again, let's assign the priorities to the substituents. The first and fourth priorities are relatively clear. But what about the second and third priorities? For those, we must invoke the equivalence system with ghost atoms. Thus, it comes down to the atoms attached to the carbons that are directly attached to the stereogenic center carbon. So on the left, as it's drawn here, we have hydrogen, hydrogen, oxygen, versus on the right, hydrogen, oxygen, ghost oxygen. Thus, it ultimately comes down to hydrogen versus ghost oxygen. Ghost oxygen is higher priority, so the left is second priority, the right is third priority. There's another trick we can employ here. It uses our hands. Now, they can't take your hands away from you in an exam, so they can't stop you doing this. Take a hand, point your thumb in the direction of the lowest priority, in this example, hydrogen. Now wrap your fingers around the remaining higher priority groups, sweeping from higher to lower. Knuckles higher priority, fingertips lower priority. Now, look at your hand. This should only be possible with one of your hands. If the hand that can do this is your right hand, the stereogenic center is R. If the hand that can do this is your left hand, the stereogenic center is S. So according to this hand method, it should be your right hand that can do this. Thus, the stereogenic center is R. Once practiced, this is a simpler way to derive an answer. So, why do I torture you with the reorientating molecules in your head? Firstly, that's a very good skill to generally have. It's applicable to other situations. And secondly, it's reassuring to have a method to double check your answer. So, let's double check this answer. We need to look at the stereogenic center from the opposite side to the lowest priority. Here, that's hydrogen. Let's move the molecule as drawn here to get in that position. So first things first, we will move the hydrogen to the back, behind the plane of paper, or in this case, screen. The hydroxyl will move across the forward face, whilst the primary alcohol and aldehyde carbonyl will make minor moves. They're not marked here. In general, it's forward. There. Let's put back the priorities. Now follow the arrows from the highest priority through the second highest priority on to the third highest priority. Okay, they're going clockwise, thus R. So happily, both methods provide the same answer. This molecule is called glyceraldehyde, the simplest carbohydrate. The IUPAC name is R plus 2,3-dihydroxypropanal, with a polarimeter value providing an alpha plus 8.7. Here, in an orientation with some similarities to the Fischer projection, is alanine. The substituents have their priorities. The lowest, fourth priority in this case is hydrogen, and is already in a suitable location to proceed, facing away from our eye, back behind the screen. So, no reorientation is required. We draw our arrow from the highest priority to the second and then the third highest priority. The arrows move in an anti-clockwise manner. Thus, the descriptor is S. What about this molecule? We're going to introduce the priorities for each substituent. Again, the lowest priority is already in a suitable position for the analysis to continue without reorientating the molecule. Next, we follow arrows from the highest priority through the second onto the third highest priority. They move in a clockwise direction, so the descriptor is R. Lastly, what about this molecule. Initially, we ascribe the priorities to the substituents. Now, here, unfortunately for us, the lowest priority, hydrogen in this case, is facing forwards towards our eye. This is undesirable for the classical methodology. But instead of mentally moving the molecule in our head, let's observe the direction of the arrows. They move from the highest priority onto the second and ending at the third highest priority. The arrows move in an anti-clockwise direction. It's standard that this would mean S. But the lowest priority is in the opposite location to what is ideal. Thus, the answer is opposite to the standard answer. Here that would be S. Thus, the descriptor in this situation is R.